when you get finally resolve, you get 6 ohms and 4 ohms. This is just one part of the photo, 6 ohms and 4 ohms. So you simply add, meaning that your total equivalent resistance is 10 ohms. So that's the end of the question.
Thank you. Does anybody have any observation to make? If you have observation to make, you are the only one to raise up your hand, or you put it on the chat box. Or is there anybody who does not understand what has been done? If you don't understand what has been done, can you please let us know? If you have challenge, I have already on the YouTube link. Somebody is asking me for YouTube link. It's already on. Oludiran is already on. Write your name properly. Oludiran, you didn't write your name properly. I shouldn't have responded to you. You didn't follow my convention. So on the account of this, do anybody ask questions or questions? So if you don't have questions, I want to move on. Thank you, Aibu. I appreciate you. You can share your screen so that we can move on. Okay, let me return to our lecture note. So we have been shown how to work this problem by two guys. We want to appreciate Matthew. Matthew started, but his screen was not able to support the work. The internet on his work could not sustain and help the work. Okay, I can see. What's your question? Alozie, can you on your mic and ask us your question?
Yeah, good morning, sir.
Yeah.
I didn't understand how where he went after adding R8 and R10. That would give us
R8 and R10.
R8 and R10, yeah.
Let me ask him to share his. Aibu, please, can you just share for the last time? Please always write question, even if your camera is not able to come up or your digital hand is not coming up. Quickly put your question on the chat box so that we don't keep going forth and back. If you had seen that on the chat box, he would have responded. Aibu, can you help us?
Okay, sir.
Share your screen again. He said he didn't know. Can you ask your question again? Alozie.
Daniel, please, can you go over what you did? Just the first line, how you went from R8 plus R10.
Okay. After you add your R8 and R10, it will then give you this combined resistance. I just repeated it as
you slanted it.
Yeah. So
I see. All right.
Parallel.
Thank you.
Okay, you are okay now?
Yes, I'm okay.
Okay.
Thank you.
Any other question? Thank you for that. I can see 2 hands up. Alozie, you can drop your hand. In Joel, can you ask your question?
Yes, sir. Good morning, sir.
Yeah.
I was asking Daniel, you told him that why did he start from the end, and then he gave you an answer. You were saying something about start from output and not inputs. I don't get why you use. I don't understand that. You said something about always start from output.
Aibu, can you focus this work again? Still focus it. Aibu, I'm waiting for you. Yes. Share your slide, your notebook again.
Sir, it's showing.
Okay, thank you. I can see it now. Now, my boy, Joseph, you because I had already given you that the question you should solve for the total resistance, which we otherwise call R equivalent. That means I take that place as my input. And there's no way I can start from R1, which is the closest to R equivalent. I have to start it from the left or the what I consider as my output. Maybe that's the word that confused you. It may not be your output in any way. It may just be a segment of the circuit, but you work it, collapsing it like that to the end until you get to where R equivalent is. For me, I would rather use my own convention that when you are solving a parallel series combination of resistors, start from your output and work it until you get to where the terminal that you are looking for the equivalent resistance. Does that make sense?
Yes, that makes sense. Thank you, sir.
Okay. Because you can't start from that R1, I think it's R1. So we must be very careful with that. Thank you for that observation that you made. So on the account of that, I want us to move fast. So there are many questions. I'm going to share this slide on my LMS. I have posted some things on the LMS for you. Once you are registered, you can go through the LMS of the university. I will not be sharing notes on the WhatsApp because anybody can be on your WhatsApp, but I will share my note on the LMS. So the university LMS, so that you can go through it. There are many questions. You can see another one, many complicated questions that I have there. This one, they are all R. The one on your left-hand side, they are all R's. But that R is 15. Each of them is 15 ohms. So I want you to resolve this. And you will go through what you already know as well to resolve this. So you will find them on the LMS. These are simpler ones, just like the question that Alozie asked. Because R equivalent is now on the left. That's why I said I will not use right or left. Because if I'm here, you should start from. Alozie.
Yes, sir.
If you are to work this problem by your right-hand side, the one on my left-hand side, where will you start?
You're going to start from the branched part of the circuit above the 2 kilo ohm. You first of all resolve that before coming down
Good
and
of you.
starting from the left.
Then when you get that,
when you get that, you start from the. You are going to start from the left hand side where 2
good of
kilo
you,
ohm.
good of you. That's great. That's great. Thank you. You got what I was trying to drive at. So I have quite a number of problems that you can still look at when you go through my LMS page. These are still resistors of different natures. These are resistors of I think we worked this last time. We worked some of this last time. I have done current divider and voltage divider method with you. We did it last lecture now. Hello,
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay. So I don't need to go through it again. I want to quickly rush to what's the name now? I want to go to, because we are talking of series and parallel circuits. Likewise, we have series and parallel circuits in inductors and capacitors, because there are three components that make up your circuits: resistors, inductors, and capacitors. So we have looked at resistors at a wider range because of the fact that they have many responsibilities in our electrical activities and electrical operations. So we want to look at inductors and capacitors. They are storage elements. They are storage elements. We use them to storage charges. And charges is what will give us current. It's what gives us voltage. So on the account of that, when you have resistors in inductors in parallel, the way you are in series, the way we have it here, and then two or more inductors in a circuit are said to be in series when the current flowing through all the inductors is the same. Just the same principle that we applied under resistance is the same principle that we are applying here again. That once there is no decision to be made, then those components, they are in series. So the same thing happens here. And you can see the way I resolve it. When you have resistors, inductors in series, at the end of the day, you have L equivalent, and you have your voltage across it. So that's how we normally resolve it. But where is the mathematical procedure for doing this? Let me go to the mathematical procedure now. The next slide. So this is the mathematical procedure for doing this. You have to remember that each of them, as you have brought, each of them has their own voltage drop. L1 has voltage drop of V1 dropping across it. L2 has voltage drop of V2 dropping across it. L3 has voltage drop of V3 dropping across it. That's how you go up to, if you have n numbers of inductors, each of them will have their own voltage drops, just like each resistance has its own voltage drop. So the total voltage drops, when you add them together, will be equal to your source voltage. You already know that one from your KVL, your KVL. So it's still applicable here. So that's how we came about the first line of our mathematical expression, which is V equals to V1 plus V2 plus V3 up to Vn. And you already know that voltage equation for inductors is L di dt. L di dt, that's the essence of bringing this in, bringing all this L di dt into to the narrative. And on their account, the IDT is the same for all of them. So you can make the IDT the subject of the formula, and you can have the L1 plus L2 plus L3 up to Ln. And those L, when you add them together, that's what gives you L equivalent here. Remember? So it is L1, L2, L3 up to Ln that gave us L equivalent here. So that's why in this place, in order to write it in canonical form and in a composite form, we have the IDT times L equivalent. In other words, our L equivalent is equal to N1, L2, L4, or L3 up to Ln added together. So this is how you do the series rest inductors. When you have inductors in series, you add all their values together. You add all their values together. You add all their values together. Alozie, any question? I can see
Yes,
your
sir.
finger
Yes, sir.
up.
Are you telling us that the IDT was equal to V in this case when writing it in canonical form?
Eh?
Are you telling us that the IDT was equal to V?
The IDT is equal to what?
V, voltage.
Eh?
Are you trying to was the IDT equal to V in this canonical representation of the equivalent inductance? Because from the first line you went V is equal to V1 plus V2, which is equal to L1 into the IDT plus L2 the IDT
Yes.
plus, and so on and so forth. Then you factorized out all the inductances and called it
Yes.
equivalent inductance L, the IDT. That DIDT,
Yes.
what does it stand for? Is it V or what? Or what?
You mean the IDT? You
Yes,
know,
yes.
look at the current. Look at the current I. It's the same current that we flow through all of them. And you know that for inductors, what makes a voltage for you to get voltage in an inductor, there must be varying in resistance, varying current with respect to time. If your current is not varying with respect to time, you can't get that. Remember Faraday's law. I hope you have not
Oh, okay,
forgotten your
sir. Yes.
Faraday's law.
No. I
When
think
you are taking your solenoid inside and outside you are taking
the
your
coil
iron inside
inside the
and
coil.
outside the coil. As you are doing that, you are pumping current, you are changing the charge, the charge. And as charges is changing according to Lenz's law, you are creating current. So we have not left those simple principles that you knew from your physics.
Right,
Does it make sense now?
yes, sir. It makes sense. Thank you.
So the same eye flows through all of them. As you can see the red arrow.
All right,
So
sir.
that's what give me the confidence to say L the I dt, L1 the I dt. I cannot use, you were expecting me to say L1, the I1 dt. But if you look at the general equation, the same current flows through all of them. So any varying in that current will affect all of them. Are you clear now?
Yes, sir.
Hello,
Thank you very
say,
much. Yes, I'm
okay,
clear. Thank you.
okay. So, and you are okay with the L equivalent value,
Yes, sir. Very okay. Thank
the
you.
expression. Okay. So let's move on. So when we look at parallel connection as well of inductors, this is what we have naturally. In this case, we apply Kirchhoff current law, voltage law with respect to the series, but in the case of inductors in parallel, we apply Kirchhoff current law. And you can see the current that Alose was trying to know why it has to remain at the IDT. You can see it here. It has been split or splitted into several branches that you have. If you have 3 branches, your original I will split into 3 others at a particular junction. And if you have more than that, it will still split. So if you look at it now, the equivalent, L equivalent, you can see it, but the current is now different. But looking at the voltage, the same voltage is dropping across all of them. I hope I am making sense to you. Let me show you for series. The voltage is the one that is divided into each of the inductor. For series, you can see V1, V2, V3. But now, with what I am showing to you with regard to parallel, is the current that is being split or that is being shared among the various branches, where the voltage is now equal for all of them. Please take note of this. It's not too different from what you know in resistances or resistance connection. So if you agree with me, remember that we now have, instead of what we had with regard to series connection, where we use voltage equation. In the case of the parallel operation, we are using current equation. You see it? You can see it. We are using current equation here. And for each current, remember, I have told you that we are following our rule with Faraday's law. And in that case, the relationship between your L and current is always what? And voltage. When you put the 3 of them together, is what we have here. So for current, it is 1 over L1 integral of V dt. And that V is constant for all of them. That's what I told you. I said the same voltage drop across all of them. It's only the current that is different. So you can see that now here. Voltage is equal for all of them. So varying in voltage with time will be equal for all of them. So if we go by that route that we have done before, we will have 1 over L. I left a step here, which is V dt, integral of V dt will be equal to 1 over L plus 1 over L2, just like we did the other time. But your final answer will still give you this. 1 over LQ will be this. This one, I need to correct this. This one is not correct. I is equals to 1 over LQ. I'm supposed to put integral V dt here. Integral V dt is supposed to be here. After 1 over LEQ, integral V dt should have accompanied it. That was an error. So the 1 over LEQ will give us what we have here. Any question, please, before I move on to capacitors? Okay, it's very clear. But I will make that correction before I share it with you. 1 over L EQ integral V. Please tell your colleagues they can enter to the YouTube. The YouTube channel is on and running. So if I give you this kind of problem, and I say, get me the L equivalent, can somebody quickly do this for me? Once you are through with it, I'm giving you just 2 minutes to do it because we are running out of time. We have not even started today's lecture. Once you have worked it, let me see your finger, digital hand. Please be fast. Get me the L equivalent. Nnamani. I can see Nnamani here. Nnamani, can you provide us answer to this? Is Nnamani in the house at all? First son of Peter. First son of Peter. All those people I'm calling that they are not responding, as far as I'm concerned, they didn't come for this lecture. All these people that wrote only their names without their matric numbers, you have not followed the rules and you have already breached the rule. The rule is that matriculation number first, surname next, other names, and then your department. Yes, Matthew, you are ready for us?
So I'm getting 14.9 million.
No, let's share your slide. Share your notebook. Share your notebook. Let's see it on your camera.
My camera is not bright.
Don't worry. Let's just see what you have. Because we will need to see what you have so that we can guide correctly and so that your mates, we are not careful that you should get the correct answer. We are careful that you know the procedure and that somebody will be blessed through your own explanation of what you want to do. So it's not a competition. So try your slide. Try to on your camera if you can.
Okay.
If you cannot, you can snap it and send it. Where do you send it now? It's only, where can you send it? You can send it to your class rep so that your class rep can display for us. You can share it on the screen like this.
Okay, sir.
If you cannot share your camera, don't worry. Send it, snap what you have done. You will still explain to us, but snap it, send it to your class rep. You are in which department, Samuel? Systems.
Electrical.
Electrical. Share it with your class rep. You should be
Okay,
able
sir.
to have a camera that can work for us.
Sir, please, can I see the question again?
Oh, you have not? That means you are not yet through with it. Yes, I can see. Ini, do you have anything for us? Ogundele, why did you on your phone? Your microphone rather. Iyade, Bello, why is your mic on? Do you have anything for us? Put off your microphone. Nobody has worked this problem 3 minutes after. This is not good enough. As we'll be seeing you competing with us, with one another, over solving this kind of problem. Ariori, if you want to do it, please unmute yourself and on your camera so that I can give you the privilege to share. You want to share it with us?
Okay, sir. Yeah.
Okay, I've dropped my own. You have the privilege now to share. Share your notebook with us and share the procedure with us.
Okay. Looking at the diagram, we can see that starting from this point, I have 100 millihenry and 40 millihenry connected in series. Then the series connection is in parallel with 50. Now the total network is in series with the 20 millihenry, and all the network is in parallel with 30. And all this network is in series with this, and all the network are in parallel with this.
Good of you.
That
Show
is
us your working.
Yeah. So 40 and 100. So that is what I just wrote here, that where the 140 is in series, and the series connection is parallel with 50. Then the 50 is in series with the 20. 20 is parallel with 30. 30 in series with 40 and parallel with 20. So I have solving this one first, which is 100 plus 40, which is 140. 140 in parallel with 50 is given by this 140 times 50, or 140 plus 50. Then plus this 20, I get 1080 over 19. Now 1080 over 19 is parallel to this 30 millihenry. So I have 1080 over 19 in parallel with this. Then the total connection is in series with the 40 millihenry. I have 656 over 11 millihenry. And after solving 656 over 20, 656 over 11 in parallel with 20, that is, I have 3280 over 219. Oh, sorry. This should be millihenry, which is equal to 14.9 millihenry.
Thank you. Does anybody have any observation, any contrary opinion with regard to what you have seen? Okay, I still have 2 hands up. Okay, Alozie, is it that you don't agree, or you agree, or you want to throw more light, or you want to ask questions? Go ahead.
I don't agree. I'm still solving it, but I think he made a mistake somewhere.
Okay, share your own. Do you have your own there? You can on your camera.
Yes, sir, but I'm not done. I'm almost done.
Okay. My own is that I would have loved someone who is not going to pack everything together at once, because you can see now Alozie is saying that there was a mistake somewhere, which is what I'm very afraid of, that it might happen. Not that the guy did not know what he's doing, but if you are taking it step by step, though he took it step by step later, but I would have loved to see that step by step, the way I have been doing my own. Though some of you are very brilliant, more brilliant than some of us, which I appreciate, and that's what the Bible says. The Bible says your children will be greater than you. So I'm not in any way, I'm even happy that I can have people who can think in a complex manner, the way some of you are thinking. I love it. I always encourage it. But I would have loved to see somebody who will want to walk my steps. I'm not saying that Ariori is wrong, though. He might still be totally correct. I still don't agree with Alozie, even though Alozie is still insisting that he has a mistake, made a mistake somewhere. Until I see where the mistake occurs, I disagree with Ariori totally. I love the way he did it in a complex manner because he has saved himself time, but there is room for errors and mistakes if care is not taken. And if you are not the type that love to go through your work again, there may be mistake. So on the account of that, I don't know if anybody has worked step by step the way I normally do it for you so that I can share with us. I can see many hands up. I can see about 5 hands up. If you want to share your own with us, please on your camera. Alozie, you are not yet through, so close your camera. Let somebody else come in. Akindele, do you want to help us? Or, okay, one of you is up now. Ojong Ayuk. Ojong Ayuk. I can't hear you. You are not speaking, but your camera is up. I can't still hear you. I can see your lips moving. I can see your lips moving seriously. You want to share something with us,
Just
but I
turn your.
can't hear you. Okay, I can hear you now. Hello, I can't still hear you. I think it's somebody interfering with us.
Turn your phone
Sorry.
upside down. I don't think it's working.
Your friend said the phone will not work the way you are doing it. Ayuk, I can't get Ojong Ayuk, and he wants to share. He's very this thing to share. Okay, I can see your note now, but I can't hear you still. He's frenetically looking for the way to just talk to us. I can see your note clearly, and you follow my steps. But my challenge is that we cannot still hear you. Or maybe I can help you to unmute you. Let me see if I can unmute you. But your camera is off here. Is this your okay, let me unmute you first to see whether you are the same person. You are the one that can unmute yourself. Oh. I can't unmute you. Sorry. And he has a very wonderful work there. I can see his work, but I cannot hear him.
Can you
And
hear
there's
me
no
now,
way
sir?
we can. Yes, we can hear you. Share
Okay,
your
sir.
notebook again.
All right.
Okay, good of you. Good of you. I love your resilience and your
Thank you,
persistence.
sir. Thank you, sir. So as you said, I started from the output, which is this the seventh inductor, which is 100 millihenry. Then I added it in series to the sixth inductor, which is 40 millihenry, which is this, to get my first equivalent, that is LQ1. Then the result of that was going to be a parallel connection with the fifth inductor, which I added in parallel here to get 700/19 millihenry. That was my second equivalent. Then the result of this was added in series to the fourth inductor. So the result of this was added in series with the fourth inductor. That was my third equivalent here. That's this plus 20 millihenry. I got this as the value. Then the result of that was added in parallel with my third inductor here, because I'm going to resolve the circuits like this. So that was my fourth equivalent here, which I got to be 216/11 millihenry. Now the result of that was added in series to the second inductor, which is 40 millihenry, and that gave me an 656 over 11 millihenry. Now, since I have resolved all my elements, I had just the 20 millihenry, and after resolving this one, I could not just take this one like this because I had a decision to either go through this part or to go through this part. So it left me with the decision that it should be in parallel. So I added it in parallel with my 20 millihenry, and it gave me an equivalent of 14.97, which I took as approximately 15 millihenry.
Okay. Ariori, what's your own opinion about this now? Does it reflect what you have done?
Yes, sir.
Okay, but you didn't get the same answer.
Mm,
Alozie, do you agree with this now?
got the same answer. Sir, we got the same answer. We got the same
Yes,
answer.
sir. I've solved this. We got the same answer. Yes,
We got
sir.
the
It's
same
correct.
answer. The answer
They
is
got the same
14.9.
answer,
Got the
Alozie.
same answer.
Yes, sir. Yes, sir. I got the same answer.
Got
I've
the same
solved this.
answer.
I finished
Okay,
solving it.
you all agree with this now. That's great. That's great.
Yes, sir.
That's great. That's what I want to see. Thank you, Ojogayu. Thank you for your persistence and resilience.
All right,
I
sir.
appreciate your this thing. Thank you. So we want to continue now. So we will move straight away to capacitance. I won't wait much time. The capacitance in series. We have capacitance in series
Sorry,
in
sir.
this
Good
form.
morning, sir.
We have
Good
capacitance
morning,
in
sir.
series in this form. Please, you cannot interrupt my lecture. I've said that you must always raise your hand.
So my hand was raised. I don't think you saw it.
Okay. What's the
Okay.
problem?
So concerning the last question, I was thinking that the last part where they solved in parallel with 20 millihenry, I was thinking that it was supposed to be added directly, as in series, but I'm not sure.
The L1.
Yes.
The L1
Yes, sir.
cannot be in series in the sense that he got a parallel after resolving L3. It's only L2 and what he got after adding L3. It can be in series. Then they will now be in parallel to L1. I worked it here. This is the answer which they all got anyway.
All right, sir.
Okay. So series connection. You already know of capacitors. You already know that for capacitors, what built between their plates is voltage. What they have built between their plates, you have the positive and negative plates. And what is there is voltage until it is full, it is shut to a level, there will be no conduction of current or flow of current or flow of charges, according to what we already know from Faraday's law. So on the account of that, when you have capacitors in series, you will have the same current flowing through them, the same way we had for inductors. But there will be different voltage drops based on the capacity or the values of the capacitors. Based on the values of the capacitors, this will determine the voltage drop for each of the, across each of the plates. And then you have the capacitors equivalent diagram as we have it on the right-hand side, just the same way we have had before. So for the capacitors, this is the equation you know very well. Some of you can even express it better than me. So V is equal to 1 over C integral of I dt. And because we have the same current, because we are talking of series, just like before, the same current is flowing through them, only different voltage drops are experienced. So on the account of that, we have 1 over C1 I dt, 1 over C2 I dt, 1 over C3, and so on and so forth. By the time you are going to write it, it's going to give you V equals to 1 over C, putting all of them together, integral of I dt, because I dt is common to all of them. And then you can get your equivalent capacitor by taking out all the capacitors and their reciprocal, the reciprocal of all the capacitors. We give you the reciprocal of capacitor equivalent. So I think that is well understood. But when you come to the parallel, you see the same scenario here, where the same current that is coming is shared to different capacitors that are in parallel. Each branch has its own branch current. So in order to write it, we are going to, instead of the series, we use the voltage equation, but in parallel, we use the current equation. And the current equation, how did it say? I equals to all the branch currents to get the total current that is in the source. And each of the current has its own definition, which is I is equal to C divided dt, from our knowledge of capacitor, C divided dt. So for capacitor 1, C1 will be divided dt because the same voltage is dropping across them. If you look at the right, the output of the first circuit diagram, the circuit diagram by your left, you see that I put V across them, and the same V will drop across all of them. Why these different currents may be experienced to flow through each of them. So on the account of that, you have dividity, C1 dividity, C2 dividity, C3 dividity, Cn dividity. And then your dividity will be will be common to all of them. So you can say I equals to C1 plus C2 up to Cn. So your equivalent capacitors now will be C1 plus C2 plus C3 up to Cn. And this, if you compare the parallel of capacitance, you can see we are adding all the capacitance together, whereas in the series, we are having the reciprocal being added together. We are having reciprocal of capacitance being added together here, but in parallel, we are having the capacitors being added together. Reciprocal is different from the normal value. Reciprocal is 1 over whatever is your normal value. Whereas for normal value is normal value. That's one thing I want you to realize. For series, it is the reciprocal of the capacitance. But if you go to the inductor, let me quickly revisit the inductor again. Look at the inductor. The series, look at the series. The series addition, look at it. You add for the inductor, the series addition is the real values. Whereas the parallel for inductor is the reciprocal. So they are opposite of each other. I don't know whether you get my drift. My point that I am trying to make is that the reciprocal, whatever you are using as your parallel in capacitors, connections, is going to be the reciprocal of it in your parallel in inductors. Under inductors, the parallel connection will give you reciprocal values. But under capacitors, the reciprocal will give you series value. Please take note of that. I don't have all the time, but I think I need to raise that observation. So in this place, your series is reciprocal for capacitors, whereas the actual value is the value for your parallel operation. So if I give you this problem and I ask you to solve it, can you please try it now? Try this problem for me. Everybody. Everybody try this problem. According to Timothy, you don't have department. I can't see department for academic Timothy, and I don't know why you are doing like this. I hope you will not give yourself problem. Please work this problem. It shouldn't take us time. I believe you have written this down before. For RC equivalent, for C equivalent for series, you have this. I believe you have done that. So for you to solve this, please. By now, as you see some people who have worked it, please let me see your hand raised. Okay. Matthew Samuel, please on your camera.
Sir, someone is sharing.
Eh?
Someone is sharing the screen. They said that I cannot share my screen while other participants.
Let me drop my own. Let me drop my own. It's my own.
Okay.
Go ahead. I've dropped my own now.
Okay, it's still not working. No.
Okay. Can you do it now?
It's working now. Camera. Okay. This is the. Okay.
We are not seeing your note yet. Okay, we are seeing you.
Okay,
we are still seeing you. Oh yeah, I'm seeing your note, but not very bright, not very legible. Yes, it's getting clearer now. It's getting clearer.
Okay.
But you are not showing the beginning of your workings. We are seeing the middle.
This is the beginning. This is the
beginning has not shown. Where your finger is, where your index finger is, Abi.
Yes, this is the diagram.
Okay, go on. You can see it.
So, I forward took it mesh by mesh.
You took your camera. It's as if your camera is facing down. It's not facing up.
Okay. It is not really bright.
Okay, it's better now. It's better now.
So this side,
you have moved away from the notebook.
Okay.
We are seeing part of your notebook, not all of it. We are seeing it now. Yes. Quite better. Maintain it like this.
Okay, no problem, sir.
You have buried it again. No, you have taken it away again.
Okay, this
Sorry.
side like this is okay.
Sorry. It's okay now. It's okay. Stop there.
Okay, no problem. I took it from this first side. I took it like this. When it is in series, you would use inverse. So I took this 1, 2, 3 inverse. That is 1/12 plus 1/24 plus 1/8 inverse. Plus the one that is in parallel in the first mesh, in the mesh 1. That is This one will give me 4, and the other one plus 4, that is 8. That means the total mesh of this side will give me 4. I'll be 8. So now the second, now if I now do the equivalent, it will now be 5, 8, and 6, because I've already used the first mesh. I found the equivalent in the first mesh. Now the second mesh, so I'll use the same something. Since it's in series, I'll do 1 plus 1 over 5 plus 1 over 8 plus 1 over 6 inverse. Then the total of everything is 2.03 microfarad.
Thank you. Is there any contrary opinion to this? Do we all agree with him? Because our time is fast spent. We need to
Yes,
move
sir.
on.
Yes,
Yes,
sir.
sir.
Okay, we are all okay. Thank
Yes, sir.
you, thank you, thank you. Thank you. You have tried severally to share with us, but you finally succeeded this time around. We appreciate you. I love this class and I love your spirit. Your spirit. Samuel, thank you. Matthew Samuel,
Thank you.
you can drop your finger, your hand now, and mute yourself. Thank you. I really love this class. So let's quickly move on. So with this now, I want to believe that we have come to the end of, you can see, this is the working of the same problem. We can see that we have come to the end of the week 2. The week 2 does not mean week 2. Maybe I should just call it lecture 2, because we just finished lecture 2. And I was thinking I won't spend this much time on this particular lecture. So I want to quickly move on now to what we should have done even before now. I want to move to our other part of the lecture, which is lecture 3. Lecture 3. Let me take us to lecture 3 and 4 together. Okay. So so we have lecture 3 and 4 together here for week 3 and week 4 lectures. So on the account of that, these are the things, if you go through the outline, lecture outline that we gave you at the beginning of this semester, you will find out that our week 3 is network theorems, week 4 is nodal and mesh analysis, and super node and super mesh must also be treated. I pray that I'll be able to rush through what I have here today and be able to complete everything. But whatever the situation, we move on. When it's 10, some 5 minutes to 10, and we have to call the lecture a day so that we can go to another lecture which starts at 10. Now, when we are talking of network theorems, we already know the KCL, we know the KVL, we know the Ohm's law, we know Lenz's law, we know the Faraday's laws, and all those things. But we have a responsibility to now apply them to some practical situations. And some of the practical situations is what we are about to do now. So I want you to read through this and probably jot some notes. So this is network theorems. The network theorems respect the Kirchhoff current law and Kirchhoff voltage law, which you already know. And I say here that Kirchhoff current law is more or less depends on the conservation of charges, because current and charge, they are interchangeable. They are interchangeable from our knowledge of Lenz's law. Then Kirchhoff voltage law is the conservation of energy.
Long, but I sent my account number to someone. You don't understand.
Who is this disturbing my class? Mute yourself once you are here. So the Kirchhoff current law state that the algebraic sum of all the current entering and leaving in an area, a system or junction is 0. That's the Kirchhoff current law. And this is depicted in this diagram. You can see all the current entry into a junction. I1 is entering into this junction. I2 is entering into this junction. I3 is leaving this junction. I4 is entering into the junction. I5 is leaving this junction. We said the algebraic sum of all of them is equal to 0. That's why you have the summation I equal to 0. So you have it like that. I1 plus I2 plus I3, 4. They all enter. So all the current that enter into that junction, we added them together. And then the one that is leaving, we minus them. We said together they all make up 0. That's what we mean by algebraic sum. However, you can now put all the one coming in on one side and not the one going out on the other side, as we have it in the first line there. So I have it again here to show it to you again. And look at this. 4 amps is going in to that system. 2 amps is leaving. 3 amps is leaving. 8 amps is coming in. So, sorry, 2 amps is leaving. 10 amps is leaving. 8 amps is coming in. By the time you use your knowledge of algebraic sum of current input and current output, here we use algebraic sum of all the current in and all the current out. And we have I1 plus I4 as in, and I2 and I3 as out. And by the time you look at it, 4 plus 8 is equal to 12. 2 plus 10 is equal to 12. So we have been able to check and confirm that Kirchhoff current law is correct. What is going in must always be equal to what is coming out. That's law of conservation of charge. So if you look at this, we still have the same situation here. I think I've given you this before. So if you are trying to look at the current, 5 amps is entering into node A. I1 is leaving node A. I2 is leaving node BA. The two of them, when they are leaving node A, we didn't give the value of I1, but you were giving the value of I2. You should be able to get the value of I1 from that. Then I2 is passing through node B, but there is no decision to be made. That means I1 that is passing through node B will still flow through R3, which means your I3 and I1 must be equal because there is no decision to be made at node B. I don't know whether you agree with me. The same thing at node C, there is no decision to be made. So the same current that flows through I2 will flow through I4. And when they come to node D, they have decision to make. And they made the decision for the R5 or I5. So on the account of that, you can see the way we resolve it here. For node A, I in is equal to I out. So I in is 5 amps. I out is I1 plus 4 amps. So we were able to get 1 amps. At node B, just like as I've said, the current is equal. At node C, the current is equal. And then by the time you get to 5, the 5 amps that you have coming in is the 5 amps that is coming out of D, node D. The 5 amps going into node A is the same 5 amps leaving node D for R5. And so this guy, I will remove you from my network. If I see any other person interrupting my lecture with spurious noise, I will not talk again. I will just delete you permanently. So on the account of that, you have what we have here, and so we can move on. So this is another problem. So you have this as well, which is Kirchhoff as well. And then the current divider rule, I've taught you this, so I don't want to run through this again. You already know it. So this is another way which I don't think I need to over labor or be labored. You already know how to split the current into various branches. I taught you this last week. Remember that when current is going into a node, we take it as positive. When current is leaving a node, we take it as negative. When current is entering a node, we take it as positive. When it is leaving a node, we take it as negative. So because I1 is entering the node, we call it positive. Because I2 is leaving the node, we call it negative. In another case, I2 is entering into the node, we call it positive. When I4 is leaving the node, we call it negative. So I think I gave you this last week. I don't want to. So these are some problems that we looked at last week. I think I showed you this as well. Kirchhoff voltage law. It means that the total voltage drop in a loop will be equals to 0 when the algebraic sum is added together. Algebraic sum of voltage drops around any loop or circuit is equals to 0. And we have sign convention, just like we have for the voltage law, a current law, the KCL, we have for voltage as well. Voltage drops are positive in the direction of the set rule. When you are following the direction, the voltage drop is said to be positive if you are following the direction of the current loop or loop current. The loop current. Our loop current, we normally take it as clockwise, and if you follow the route, you take it as positive. But voltage drop is negative when it is opposing the loop current. When it is opposing the loop current. We worked a problem like this last week. Voltage source positive if the current flows out of it. If current is flowing out of its voltage source, it is considered as positive. If it is flowing into the voltage source, it is considered as negative because source is supposed to make supply available. So if it is one receiving, then it is taken as negative. So I think we look at this as well as voltage divider rule. So this is a typical problem. And this is a node, common node. So we already know that for this, if you are dealing with it with nodal analysis, you will have the current flowing out that way. So we want to move to nodal analysis now. We have been able to establish the voltage current Kirchhoff voltage law and Kirchhoff current law. The two of them are going to be very much useful when we are dealing with nodal analysis and mesh analysis. So the nodal analysis from the information that I have shared in the previous slides provides a general procedure for analyzing circuit using the node voltages as the current circuit variables. The circuit variable that we normally use is the nodal voltages or node voltages. Choosing node voltage instead of the element voltage as circuit variable is convenient and reduce the number of equations that we will have. So when we use the node voltages, it makes our work more convenient than using the other form of approach, which is the element voltages. So the rules that apply to nodal analysis is that to determine the node voltage, you select a node as the reference node. You must always have a reference node and then assign voltages to other nodes except that one. that is reference node. So if I have 4 nodes in my circuit, I will take one of the nodes as my reference nodes, and the other 3, I will label them as V1, V2, V3. V1, V2, V3 for a 4-node circuit. And then we apply our Kirchhoff current law. That's why we review the current law again. That's why we review the current and voltage law again. I know we did it last week, but I have to review it because of where we are going to. So you use the Kirchhoff current law for nodal analysis because you are dealing with node. And remember that when I said you are dealing with node, I showed you a picture here. Let me go back to that picture. Because we are dealing with node, this particular convention becomes very, very crucial to us. This convention becomes very, very crucial to nodal analysis. So please don't forget that approach. So then you solve the resulting simultaneous equations. If you have 3 nodes, you have 3 equations or thereabout. And you must be able to know how to use your Ohm's law alongside with it. So let's see, a typical example is here. We ask that we should consider this circuit. You have I1, I2 as your current sources. And you have a number of resistors there, R1, R2, R3. So if you take node 1, node 2, there are 3 nodes here. There are 3 nodes here, node 1, node 2, and the one that has the earthing. The one that has the earthing is another node. So because we have a 3-node circuit, one of them must be reference. So it is only 2 that we have other nomenclature or numbering. If I can use that, we can give it, tag it, or label them as numbers. But one will be a reference node out of the 3. So it's only 2 nodes that you have to evaluate. So we now have 1 at junction 1, which is the where I1, I2, R1, R2, they have a common node there. And then you have the junction 2, where R2, R3, and I2, they have a common node. So if you are to do that, we move to the arrow. You can see the arrow. At this point now, the direction of the current has now been established by you. And I told you, don't worry. If you made wrong mistake in the direction of your current, it will reflect when you get your final answer. If you get your final answer as negative, you know that the direction is positive, is to be reversed. If you get positive, that means your direction that you have chosen is correct. So that's the only thing. It will not change the value of your answer. So on the account of this, we say I1 is going out of that node 1, I2 is going out of that node 1, and another I is entering into R2. So if you look at another R is entering into R1, whereas this source current, I will remove this guy straight away. It's not supposed to be in my lecture. So as I said before, please don't make noise in this class. If you make noise now, I will send you out of the classroom straight away. I'll send 2 guys out now. So you can see what we have here. The current on the source current I2 is leaving that node. The current source I1 is entering that node 1. Whereas the resistors, R1 and R2, they are drawing current and they are leaving that node. Their current directions are leaving that node. So all of them put together, we have node 1 equation as we have it here. I1 is entering, but I1, I2 for the resistors, and capital I2, they are leaving. Based on our rule of KCL, algebraic sum will be equal to 0, but the current entry, you can add them together. The current leaving, you can add them together. That is what we have done. Somebody may ask me, why do you have I1, I2 twice? Look at it closely. We have the uppercase I and lowercase I. The uppercase I's are the one for the sources, current sources. While the lowercase I's, they are the one for the resistors, the current flowing through the resistors. So please don't confuse them. Uppercase I's are for the current sources, while lowercase I's are the one that is flowing through the resistors. Thank you. So you have, for node 1, you have what we put here. For node 2, look at node 2 again. I2 is entering into node 2 from the resistor. I2 from the current source is entering into node 2. But I3 for resistor, R3 is leaving. So the one entry, you add them together, and the one leaving, you add them together, and you put an equation, equality sign. So that's how we arrive at these two equations. So we have two nodes, we have two equations. We have two nodes, we have two equations. Please take note of that. You must have the number of nodes. The number of nodes will determine the number of equations you will have. After you have removed that of reference node from it. Your reference node is always 0. Voltage will be 0 there. That's why if you look at our original equation, our original circuit diagram, you will see that 0 is meeting where you have the reference node. Please take note of that. So you have this. Still on that case, it's still the same diagram, and the current I, V higher minus V lower, is over R, will give us current. Please take note of that as well. That's for our KCL. The higher voltage minus the lower voltage divided by resistor value will give you your current. Will give you your current. Please write this down. You may not see it in many textbooks. Okay, if you maintain this general equation for V higher minus V lower over R, let's take I1. The current that will flow through the resistor R1, I1, the lowercase I, 1. Let's look at it. The voltage is V1. We have already said that the reference is 0. So we can say V1 minus 0 over R1. That's our I1. Look at I2 as well. Lowercase I2. We have V1 and we have V2 on both sides of the resistors. So the voltage on the V1 will be higher than that one on the V2 side. So we can say V1 minus V2 over R2. Because why do I say the voltage on the V1 side will be higher? Because current flows in the direction of lower potential. We say water flow downhill. River does not flow uphill. River flows downhill. Take note of that. The same way current flows downhill. I shared the testimony with you during our first or second lectures that every student wants the easier way out. Easier way to know how to pass their exam, not an illegal way, even still in legal way. They want to see Give me a problem. I want to, instead of spending 10 minutes to solve it, can I get a way that will make me to solve it in 3 minutes until get my full answer? So everybody looks for easier way out, not easier way in quote of being a lazy person, not easier way of being a weird person, not easier way of being a criminal in our way of doing things. Even when we want to do legal things, we still want the easier way out. Easier in the sense that instead of sweating, what I can spend 2 minutes to do, why must I spend 10 minutes to do it? When I can get the remaining 8 minutes in some other useful endeavors. So it is normal in nature. So the current flows downhill. The river flows downhill. So the current we always want to flow from higher potential to lower potential. So on the account of that, that's why I can confidently and boldly say that V1 is of higher value or it's an high yield and the V2 is a low yield level. Please take note of that because I don't want it to confuse you. So I3 is taken for granted. All of us know that reference node is 0. So V2 will always be higher than reference node. So that's how we got that. So if you put that to work, looking at my right-hand side, you will see that I went further to say I1, all the current in I1, the source current is I1. And other current that is flowing out is uppercase I2, which is reflected in the equation on your right-hand side of this slide. I2 is there, uppercase I2. Then lowercase I1, which is V1 over R1 that we just calculated. That's why you have V1 over R1. Then the next one is lowercase I2, which is the difference between V1 and V2 over R2. Difference between V1 and V2 over R2. So when you add all of them together, you have gotten the current, the nodal analysis of that node. You have been able to get something for it. The same thing for node 2. For node 2, there are 2 currents flowing into the node 2. Which one are these currents? The current for lowercase I2 is flowing in. The current for uppercase I2 is flowing in, but lowercase I3 is flowing out. Lowercase I3 is flowing out. And if you look at our equation, uppercase I2 is being depleted and lowercase I2, remember lowercase I2 is V1 minus V2 over R2. Sorry, the equation, the second term, I'm not correct with the second term. I'm supposed to write V1 minus V2 over R2. I will correct that before I share it with you. V1 minus V2 over R2, not V1 minus V2 over R2. Take note of that. It's V1 minus V2 over R2. So it will be equal to V2 over R3, which is the output. Which is the output. That's V2 over R3. Because the reference node is already 0, so you don't need to take account of it. Yes, I can see 2 fingers, 2 hands up. Yes, Abolade, what do you want? And thereafter,
Okay, so I want to ask that which you were explaining higher potential and lower potential. I did not really get the explanation.
I don't know whether you have ever been to any river before, but if you have
Yes,
been
sir.
to river, you will see that water flows from higher potential, high height to lower height. And that is what we call potential. From higher level to lower level. That's the same way current flows. It will flow from where there is more current to where there is lower current or lower resistance. And when there is lower resistance, then the current will be low.
Okay, sir.
Do you get it now?
Yes, sir.
Okay. And that's exactly the way all of us wants to work. That's what I mean by that. You can drop your hand. Hello, Zie. Can I
Yes,
hear
sir.
you as well?
Why is in that second equation you said big I2, that's like I2 plus V1 minus V2 over R2 is equal to V2 over R3. Why is V2 over R3? It does not correlate with. Is it because V2 is flowing into R3 or what?
Okay, good of you. If you look at our diagram, that's why I made a small microcosm of the original diagram given to us. That's why I made it available by the side. You can see the arrow that are entering. How many arrows are entering to that node 2?
There are two arrows on
Can
entering
you
into node
mention
2.
them?
I2. There is I2 and there is
That's the uppercase
I3.
I2 or lowercase I2.
Lowercase I2, uppercase
Yes.
I2, and
Yes.
lowercase I3.
Where is
Lowercase
lowercase I3 going? Is
lowercase
it coming in
I3
or going out?
is flowing out of node 2 into R3,
So
into
what?
resistor 3.
Thank you. What is the principle I gave to you? I said summation of all the current coming in is equal to summation of all the current
Current
going
going
out.
out. Yes, sir.
I can still show it to you if I can still see it under KCL. Sorry, I think I have passed it. Under KVL rather. KCL. Lowercase. Look at this. Total current, summation of all the current coming in, that's I, uppercase I in. That I, subscript I means in. Summation of all equals to summation of current O, IO. That O stands for output. So total current coming in equals to total current going out. That's why I laid this foundation before we went to that. Does it make sense to you now, Anozie?
Yes, sir, it does. Thank you.
Yeah, so that's why I have corrected myself here that V1 should not stand alone. It should be V1 minus V2 over R2. That R2 should cover all of them because that's how we got I2 in the first place for the lower case. So it was an error in typing that I made here. I will correct it and I will revert. So that's the essence of V2 over R3 is the only one flowing out. If you go along with what I just showed to you about KCL, it's only I3 that is flowing out, while I2 and lowercase I2 and uppercase I2, they are flowing in. Does it make sense now? Alozie?
Yes, sir, it makes sense. Thank you.
Okay, thank you. So let's move on. Alozie, you can mute yourself. So this, another one, but I may not be able to go through this one because of time, having explained painstakingly that other one. I don't see you have a problem with it any longer. Still on nodal analysis. Your nodal analysis, you can come to a situation where when you want to analyze your nodal analysis, you may need to use different methods. So there are, under nodal analysis, you can solve whatever number of equations I've told you. If you have two nodes, you will have two equations. If you have three nodes, except your reference node, you will have three equations. You may have a number of nodes that will give you equations that you will need to use a number of mathematical analysis approach or approaches. one of the methods that you can use to get your values for each of your terms that you want to get is called elimination technique. You have used this severally in your undergrad, in your secondary school days. In your year one, you have used them. They are not things that are difficult. What do we mean by elimination method? You have two equations. You will add certain things to one so that you can make up for the second, and so that you can solve for one and eliminate the other one. Like in these two equations that we wrote here, equation 1 and equation 2, you can use elimination method to get V1 and V2 here. And the elimination method, you may decide that 3V1 minus V2 equals to 20, and minus 3V1 plus 5V2 equals to 60. You already have a, a value that we can call equal value as your terms. On the account of this, you may decide to just add the two of them. One is minus 3V1, the other one is plus 3V1. You may decide one way or the other to add the two of them. If you add the two of them, V1 will be eliminated totally from these two equations, so you will be left with only V2. And that V2 will give you the answer. So you have eliminated V1. As you have gotten V2, you can now get the value of V1 using either of the two equations. That's what we mean by elimination method that you see here. I hope I am making sense. That's how we got this. Then there is another method called the Cramer's rule. Cramer's rule is an offshoot of matrices or activities. Matrices activities. So on the Cramer's rule, you have to put your matrices into action. And in doing that, you can see what has been done. And I am sure that you have used some of this in the previous, in your year one. You have learned a number of these things, and you have always been using them. So please, you can see how we got V1. V1 is equal to D1 over D, where your V1, D1 is replacing. You can see how you got your D, and replacing the first column by your 20 and 60. And then you will get it this way. The same way V2, you replace the second column with the value of your equality, and then you get the other one, which is V2. And the answer you will get here will be the same with the answer you get for elimination method. Our time is spent. I think we are going to stop on this nodal analysis, and we continue from mesh analysis. No, supernode. We will need to do supernode before we move to mesh analysis next week. Can you quickly draw these diagrams? Find the voltages at the three non-reference nodes. Here we have 4 nodes, but 3 are non-reference nodes. Why 1 is reference node? Please draw this in the next 2 minutes. My time is up for your lecture. This is where we will start from next lecture. I want to give you one more question. I want to believe you have taken this. So this is the second question. In this place, I want you to calculate the voltage Vx using nodal analysis approach. use nodal analysis, where R1 is 5 ohms, R2 is 2 ohms, R3 is 4 ohms, and Vs is 10 volts. That's number 2. Number 3 is this. Find nodal voltages. The voltages are the non-reference nodes. And I have given you R1, R2, R3, and R. Oh, I didn't give you R4 and R5. R1, R2, R3. Okay, I didn't give R5 and R4. Let your R5 and R4 be equals to 10 ohms. Please put 10 ohms as your R4 and R5. Ten ohms for R5 and R4 and R5. And Vx1 and Vx2. Vx1 and Vx2. Vs1 is 10 volts. Vs2 is 15 volts. Vs1 is 10 volts. Vs2 is 15 volts. So I think with these 3 problems, you should be able to have been able to get to somewhere. So we will start from supernode from next lecture. So our next lecture is 3rd of December.
Please, can we see the second question again?
Okay. This question?
Yes, sir. Thanks, sir.
Can we start leaving, sir? Is the class over, sir?
Before you leave, let Vx. Okay, I think you should be able to resolve it. We can begin to leave now. Thank you. It's already 10. I even have another lecture. So have a
Okay,
great
sir.
time. See you next week.
But is there any value for I5?
I gave it as a I4 and I5. I gave them as 10 ohms.
10 ohms.
I4
Yes,
and
R4 and R5 together.
10 ohms.
Each of them is 10 ohms.
Sir, please, when is this going to drop on the LMS?
I have dropped some notes for you there. So go through the LMS. I want to be sure you can access it. Because the year 5 are telling me that they cannot access my page. So that I can tell the CITS people. So let
Yes,
your
sir, we
class
can.
rep know, or you just
Phone
send
and
me
wait.
WhatsApp. You already have my number. Let me know if you can access the LMS. So thank you for your audience. Have a great time. So see you next week again.
Thank you, sir. All right,
So I'm
sir.
closing this lecture because I need to go to year 5 class.